Hello there and welcome. Tonight's peaceful journey takes us beyond our small blue world, past the familiar glow of our sun, into the vast island universes we call galaxies. These magnificent stellar cities drift through space like glowing embers in an infinite darkness, each one home to billions of stars and countless stories. But before we float among these cosmic islands, I'd love to know, where are you watching from tonight? And when you look up at your patch of sky, what do you see? Perhaps a few scattered stars, maybe the faint ribbon of our own galaxy's edge. How perfectly fitting. Here we are, tiny beings living inside one of these cosmic giants, trying to understand what we're truly part of. It's remarkable, isn't it? How we can feel so grounded here on Earth, feet firmly planted on solid ground, and yet we're actually passengers on a small rocky world that's spinning through space at tremendous speeds, orbiting a star that's itself racing around the center of a galaxy containing hundreds of billions of other stars. Right now, as you settle in for the evening, you're traveling at about 230 kilometers per second around the galactic center, completing one enormous orbit every 225 million years. The last time our solar system was in this exact position relative to the galaxy's center, dinosaurs were just beginning to diversify and spread across the planet. It's a dizzying thought that puts our daily concerns into a rather cosmic perspective. When ancient humans looked up at the night sky, they saw the same band of light we call the Milky Way, that ghostly river stretching across the darkness. But they had no idea they were seeing their own galactic home from the inside. To them, it might have been the path of souls, or milk spilled by the gods, or perhaps the spine of the night sky itself. They couldn't have imagined that each tiny point of light was actually a massive ball of nuclear fire, some larger than our own sun, burning for millions or billions of years in the vast cosmic deep. And they certainly couldn't have conceived that beyond what they could see lay countless other galaxies, each a stellar metropolis in its own right, stretching away into distances so vast that light itself takes billions of years to travel between them. Tonight, as we embark on this gentle exploration of what galaxies really are, we're continuing a journey of understanding that began with those first curious humans who looked up and wondered. We're fortunate to live in an age when we can peer deeper into space than ever before, when telescopes both on Earth and floating in the cosmic void can capture light that has been traveling toward us since the universe was young. We can see galaxies as they were billions of years ago, watching the cosmos grow and evolve, witnessing the birth and death of stellar empires across time scales that make human civilization seem like a brief flicker. But perhaps what's most wonderful is that this isn't just an academic exercise in astronomy. Understanding galaxies helps us understand our own cosmic story, our place in the grand scheme of things. Every atom in your body was forged in the heart of a star somewhere in our galaxy, cooked by nuclear fusion, and then scattered into space when that star died, eventually finding its way into the gas cloud that would become our solar system. You are, quite literally, made of star stuff that has been cycling through the galaxy for billions of years, and you'll continue to be part of that cosmic recycling long after your current configuration of atoms has moved on to other adventures. There's something deeply comforting about this perspective, especially as the day winds down and we prepare for rest. We might feel small when we contemplate the scale of galaxies, but we're not separate from them. We're integral parts of their ongoing story. Our galaxy has been nurturing and creating for over 10 billion years, slowly building up the heavier elements necessary for rocky planets and complex chemistry, setting the stage for the emergence of life and consciousness. In a very real sense, the galaxy gave birth to us, and now, through us, it has developed the ability to study and understand itself. So as we begin this cosmic voyage together, remember that you're not just an observer looking at distant stellar systems. You're a temporary arrangement of galactic material that has somehow organized itself into a form capable of wonder, curiosity, and the desire to understand its origins. Your thoughts, your dreams, your capacity to feel awe at the beauty of the universe, all of this emerged from the same processes that shape galaxies, from the same fundamental forces that bind stars together and drive the cosmic dance of matter and energy across space and time. Whether you're watching from a bustling city where only the brightest stars peek through the glow, or from a dark countryside where the Milky Way spreads across the sky like a cosmic river, you're sharing this moment with countless other points of consciousness scattered throughout our galaxy and beyond. Each of us a brief flickering of awareness in the cosmic story, yet each of us carrying within our minds the ability to comprehend and appreciate the vast stellar community we call home. If you find this starlit voyage soothing, or if the gentle mysteries of space help quiet your mind after a long day, I'd be ever so grateful if you gave this video a like and perhaps subscribed. It helps this little corner of cosmic calm reach others who might need a peaceful pause beneath the stars. There's something deeply therapeutic about contemplating the larger universe, isn't there? When the concerns of daily life feel overwhelming, when deadlines loom and responsibilities pile up like cosmic dust, it can be wonderfully grounding to remember that we're part of something so much larger and more enduring than our immediate worries. The galaxy has been here for over 10 billion years, patiently nurturing countless generations of stars, and it will continue long after our brief human moment has passed into the cosmic background. Now, I do hope this isn't so fascinating that it keeps you awake, though if it does, at least you'll drift off knowing you're part of something breathtakingly vast and ancient. There's a beautiful irony in using the contemplation of infinite space as a pathway to sleep, but perhaps it makes perfect sense. When we truly grasp our place in the cosmic order, our individual anxieties begin to feel less urgent, less pressing. Not because they don't matter, they absolutely do matter to us and to those we love, but because they exist within a context so grand and so patient that we can afford to let them rest for a while, to give our minds permission to simply be present in this moment, floating through space on our small world, cradled by the gentle gravitational embrace of our galaxy. So settle in, let your breathing slow, and prepare to discover what it truly means to live inside a galaxy. Allow your shoulders to relax. Let your thoughts begin to soften around the edges. Tonight, instead of counting sheep, we'll be counting stars. Not literally, of course, because that would take far longer than a human lifetime, but metaphorically, gently, allowing the rhythm of cosmic processes to sync with the rhythm of your own body settling into rest. Somewhere between starlight and silence, between the familiar and the infinite, lies one of the universe's most beautiful secrets, and we're about to explore it together. Think about this for a moment. Every peaceful breath you take contains oxygen atoms that were manufactured in the cores of massive stars billions of years ago. These atoms have traveled countless light years, perhaps cycling through multiple stellar generations, before finding their way into the water and air of our planet. And now, for this brief cosmic instant, they're part of you. In a few moments, you'll exhale them back into the atmosphere, where they'll begin another chapter of their galactic journey. We're not just observers of the cosmic story, we're active participants in it, temporary patterns in the endless dance of matter and energy that defines galactic existence. The galaxy is patient in ways that can teach us about patience. Stars form over millions of years, live for billions of years, and die in processes that span eons. Spiral arms sweep around galactic centers over hundreds of millions of years, carrying stellar nurseries and planetary systems on journeys so vast that entire evolutionary lineages rise and fall during a single orbit. This perspective doesn't diminish the importance of our human-scale experiences, our loves, our dreams, our daily joys and sorrows, but it does place them within a context that can be profoundly calming. We're part of something that operates on timescales so grand that our most persistent worries are less than fleeting whispers in the cosmic conversation. There's also something wonderfully democratic about our galactic citizenship. Whether you're watching from a penthouse apartment or a rural farmhouse, from the northern tundra or tropical beaches, you're equally a part of this vast stellar community. The same galactic processes that created the elements in distant stars also created the elements in your hometown soil, in your morning coffee, in the device you're using to watch this video. We all share the same cosmic heritage, the same stellar ancestry, the same fundamental participation in the galaxy's ongoing story of creation and evolution. As we prepare to dive deeper into the nature of galaxies, let yourself feel the gentle motion of our cosmic journey. Right now, our entire solar system is gliding through space at hundreds of kilometers per second, following an orbital path around the galactic center that we've traveled countless times before. It's a journey so smooth and vast that we can't feel it directly, but it's always there, a constant, gentle acceleration that carries us through the cosmic deep. Allow that motion to rock you gently as we explore the stellar cities that fill the universe, each one a unique experiment in gravity, time, and the endless creativity of cosmic processes. Tonight, let the galaxy sing you to sleep with its ancient lullaby of spinning stars and slowly dancing dark matter, a song that's been playing for billions of years and will continue long after our current concerns have faded into the peaceful darkness of cosmic time. When you step outside on a clear, dark night and look up, you might see what appears to be a faint, cloudy band stretching across the sky, the Milky Way. For thousands of years, humans have gazed at this ghostly river of light and wondered what it could be. The ancient Greeks called it Galaxias Kyklos, meaning milky circle, which is where our word galaxy comes from. They thought it might be the pathway where souls traveled to the afterlife, or perhaps spilled milk from the breast of the goddess Hera. The Romans saw it as a road through the heavens, while various Native American cultures described it as the path of spirits or the backbone of the night. But what you're actually seeing is our galaxy from the inside. Billions of distant stars so far away, they blur together into that soft, luminous stream. It's like trying to understand a vast city while standing in the middle of it. You can see lights and movement, but the true scope remains hidden. This perspective problem plagued astronomers for centuries. Imagine being dropped into the middle of London or Tokyo at night, with no map, no guidebook, and no way to rise above the streets to get an overview. You'd see lights stretching in every direction, buildings of different heights and ages, busy intersections and quiet side streets, but you'd have no sense of the overall layout, the neighborhoods, the parks, or how all the pieces fit together into a coherent whole. That's essentially what we're dealing with when we try to understand our galaxy from our position within it. We're about 2/3 of the way out from the center, embedded in what we now know is a spiral arm, surrounded by gas and dust, that blocks much of our view of the galactic center and the regions beyond. For our ancestors, this band of light was mysterious and inspiring, but they had no way to know that each point of light was actually a distant sun, possibly accompanied by its own family of planets. They couldn't have imagined that some of those stars were newborns, just a few million years old, and blazing with the fierce blue-white light of youth, while others were ancient red giants in their final stages of life, having burned steadily for billions of years. Some were explosive variables, flaring up and dimming down in regular cycles, while others had already died and collapsed into white dwarfs, neutron stars, or black holes. their stories written in the elements they scattered into space during their final moments. The seasonal changes in what we can see of the Milky Way tell their own story about our cosmic situation. In summer, when we're looking toward the galactic center, the Milky Way appears brighter and more dramatic, densely packed with stars and dark lanes of dust that create intricate patterns across the sky. In winter, when we're looking outward toward the galactic edge, it appears fainter and more diffuse. It's as if we're living in a cosmic suburb, and depending on the time of year, we're either looking downtown toward the bright city center or outward toward the quieter residential areas and eventually the cosmic countryside beyond. But our ancestors were remarkably good observers, even without telescopes or modern instruments. They noticed that the Milky Way had structure. It wasn't just a uniform glow, but showed variations in brightness, dark patches where something seemed to be blocking the light, and regions where it split into multiple streams. They tracked how it moved across the sky throughout the night and throughout the year, noting that it seemed fixed relative to the other stars, suggesting it was part of the same cosmic framework rather than something separate floating in front of or behind the stellar backdrop. The invention of the telescope in the early 1600s began to reveal the true nature of this mysterious band. When Galileo turned his primitive instrument toward the Milky Way, he was amazed to discover that it resolved into countless individual stars, so many that they were impossible to count. This was the first hint that we were dealing with something vast beyond imagination, a collection of stars so numerous and so distant that they blended together when viewed with the naked eye. It was like looking at a distant swarm of fireflies and suddenly realizing that each point of light was an individual insect, not a continuous glow. As telescopes improved over the following centuries, astronomers began to map the structure they could see, noting that stars seemed to be distributed in certain patterns, with some regions much denser than others. They discovered that many of the fuzzy patches they could see through their telescopes, what they called nebulae, were actually distant collections of stars so far away that even their most powerful instruments couldn't resolve them into individual points of light. But a crucial question remained. Were these distant nebulae part of our same stellar system, just very far away, or were they separate systems altogether? This question would dominate astronomy for nearly 2 centuries, with passionate arguments on both sides. Some astronomers believed that everything they could see was part of one enormous stellar system with our sun somewhere near the center. Others suspected that some of the spiral nebulae they observed might be separate island universes, but they had no way to prove it. The distances involved were simply too vast to measure with the techniques available at the time. Meanwhile, photographers began capturing long-exposure images of the night sky, revealing details invisible to the human eye even through telescopes. These photographs showed that the Milky Way had incredibly intricate structure, dark lanes and bright patches, areas where new stars seemed to be forming in glowing clouds of gas, and regions where older stars clustered together in dense groups. The galaxy began to reveal itself as a dynamic, complex entity, not just a static collection of lights, but an active, evolving system where cosmic processes played out over timescales far longer than human experience, but clearly visible in the patterns of light and dark spread across the sky. It wasn't until the 1922nd that we truly understood what galaxies are. An astronomer named Edwin Hubble, using what was then the world's largest telescope at Mount Wilson Observatory in California, made a discovery that changed everything. He found that the fuzzy spiral nebulae scattered across the sky weren't just clouds of gas within our own stellar neighborhood. They were entire galaxies, island universes, as they came to be called, each containing billions of stars. Suddenly, the universe became unimaginably larger. Our Milky Way wasn't the entire cosmos. It was just one galaxy among countless others. Like discovering your hometown is actually one small island in an archipelago that stretches beyond every horizon. The realization was both humbling and magnificent. We live in just one stellar city among billions, each separated by vast gulfs of nearly empty space. Hubble's breakthrough came through his patient observation of a particular type of star called a Cepheid variable. These remarkable stellar lighthouses pulse with a regular rhythm, growing brighter and dimmer in cycles that can last days or weeks. What makes them so useful is that their period of pulsation is directly related to their actual brightness. The longer the period, the more luminous the star. This relationship, discovered by astronomer Henrietta Swan Leavitt through her meticulous study of variable stars in the Small Magellanic Cloud, provided astronomers with a cosmic measuring stick. By observing how bright a Cepheid appeared compared to how bright it should be based on its pulsation period, astronomers could calculate its distance with unprecedented accuracy. When Hubble found Cepheid variables in the Andromeda Nebula and calculated their distance, the results were staggering. Andromeda was nearly 1 million light-years away, far beyond the boundaries of our own galaxy. This wasn't a nearby cloud of gas and dust. It was an entirely separate stellar system, containing its own billions of stars, its own structure, its own story of cosmic evolution. The implications rippled through the scientific community like shockwaves. If Andromeda was a separate galaxy, then by extension, the thousands of other spiral and elliptical nebulae visible through telescopes were likely separate galaxies as well. The scale of this revelation is difficult to overstate. Before Hubble's discovery, most astronomers believed the universe consisted of our galaxy alone, with everything else being relatively nearby objects within our cosmic neighborhood. The known universe suddenly expanded by a factor of millions. It was as if humanity had been living in a single house, believing it to be the entire world, only to step outside and discover a vast city stretching to every horizon, filled with millions of other houses, each with its own inhabitants and histories. This discovery also solved a long-standing puzzle about the distribution of these nebulae in the sky. Astronomers had noticed that spiral nebulae seemed to avoid the plane of the Milky Way, clustering instead toward the galactic poles. This had led to various theories about why our galaxy might be repelling these objects, or why they might prefer certain regions of space. But once it became clear that these were separate galaxies, the pattern made perfect sense. The dark lanes of dust in our galaxy's disk were blocking our view of distant galaxies in those directions, just as fog might hide distant mountains when you're looking across a valley. We could see other galaxies most clearly when looking perpendicular to our galaxy's disk, where the dust thinned out and provided clearer windows to the cosmic deep. The realization that galaxies were separate systems also explained their variety of forms. Some appeared as elegant spirals with graceful arms sweeping out from central bulges, like cosmic pinwheels frozen in space. Others were smooth ellipticals, ranging from nearly circular to highly elongated, filled with what appeared to be older, yellower stars. Still others were irregular in shape, with no clear pattern or symmetry, as if they were either very young systems still organizing themselves or ancient galaxies that had been disrupted by some cosmic encounter. Each type told a different story about how gravity, gas dynamics, and stellar evolution could shape matter on galactic scales. Hubble went further, developing a classification system for galaxies that astronomers still use today. Spiral galaxies were subdivided based on how tightly wound their arms appeared and how prominent their central bulges were. Ellipticals were classified by their apparent flattening, from nearly spherical to quite elongated. This classification system revealed that galaxies weren't random arrangements of stars, but organized systems with distinct structural properties, suggesting that fundamental physical processes governed their formation and evolution. Perhaps most remarkably, Hubble discovered that the more distant a galaxy appeared, the faster it seemed to be moving away from us. This observation, known as Hubble's law, provided the first clear evidence that the universe itself is expanding, carrying galaxies apart like raisins in rising bread dough. The implications were profound. If galaxies are moving apart now, they must have been closer together in the past. Tracing this expansion backward led to the revolutionary idea that the universe began in an extremely hot, dense state, what we now call the Big Bang. The discovery of other galaxies also raised fascinating questions about life in the universe. If our galaxy alone contained hundreds of billions of stars, and there were billions of other galaxies, each with their own stellar populations, then the universe suddenly became a place of almost infinite possibility. How many planets might orbit those distant stars? How many might have conditions suitable for life? Were there other forms of consciousness looking back at us from distant galaxies, making their own discoveries about the cosmic architecture that connected us all? This expansion of our cosmic perspective happened remarkably quickly, compressed into just a few years of astronomical observation and analysis. It was as if humanity had been granted cosmic vision overnight, able to see beyond the boundaries of our stellar neighborhood into a universe far grander and more complex than anyone had imagined. The lonely galaxy we thought we inhabited was suddenly revealed to be part of a vast cosmic community, each member following its own evolutionary path through space and time. So what exactly is a galaxy? At its heart, a galaxy is a gravitationally bound collection of stars, gas, dust, and that mysterious substance we call dark matter, all held together in a cosmic dance that's been going on for billions of years. Think of it as a stellar city with different neighborhoods, dense downtown cores where older, redder stars cluster together, sprawling suburbs in the spiral arms where young, blue stars are still being born, and quiet outskirts where only the occasional star wanders in the cosmic countryside. Most galaxies contain anywhere from millions to trillions of stars, along with vast clouds of hydrogen and helium gas that serve as stellar nurseries, and tiny particles of cosmic dust that, despite their name, play crucial roles in star formation and give galaxies their beautiful varied colors when viewed from afar. The stars themselves are like the citizens of these cosmic cities, each with their own life story, age, and role in the galactic community. The oldest residents are the red giants and red dwarfs, ancient stars that formed when the galaxy was young and have been steadily burning their nuclear fuel for billions of years. These stellar elders tend to cluster in the central regions and in globular clusters that orbit the galaxy, like cosmic suburbs populated entirely by retirees. They've seen the galaxy evolve, witnessed countless stellar births and deaths, and carry within their atmospheres the chemical signatures of the galaxy's early composition, mostly hydrogen and helium left over from the Big Bang, with only trace amounts of heavier elements. Then there are the middle-aged stars like our own Sun, settled into steady careers of nuclear fusion, burning hydrogen into helium at a predictable rate that will sustain them for billions of years. These stars often have planetary families, rocky worlds, and gas giants that formed from the leftover material of stellar birth. They're found throughout the galaxy, but are especially common in the disk regions, where there's been enough time for stellar generations to enrich the interstellar medium with the heavier elements necessary for planet formation. The young stars are the galaxy's teenagers, hot, blue, and energetic, burning through their nuclear fuel at prodigious rates. These massive stars live fast and die young, often in spectacular supernova explosions that can briefly outshine their entire galaxy. They're typically found in the spiral arms, where the galaxy's rotation has compressed gas clouds and triggered new rounds of star formation. Their intense ultraviolet radiation ionizes the surrounding gas, creating the beautiful nebulae that glow like cosmic neon signs, advertising the locations of stellar nurseries. But stars are just one component of the galactic anatomy. The space between stars isn't empty but filled with an incredibly thin mixture of gas and dust called the interstellar medium. This material, though rarefied by earthly standards, often less dense than the best vacuum we can create in laboratories, is the raw material from which new stars form and the repository for the ashes of stars that have died. The gas is mostly hydrogen and helium, but it's been gradually enriched over billions of years with heavier elements manufactured in stellar cores and dispersed by stellar winds and supernova explosions. The dust component consists of tiny solid particles, typically smaller than the particles in cigarette smoke, composed of silicates, carbon compounds, and frozen gases. These dust grains might seem insignificant, but they play crucial roles in galactic ecology. They absorb starlight and re-emit it at longer wavelengths, creating the dark lanes we see silhouetted against the Milky Way. They also serve as condensation nuclei, where gas atoms can stick together, facilitating the formation of molecules and eventually the gravitational collapse that leads to new star formation. Perhaps most remarkably, galaxies appear to be embedded in vast halos of dark matter, an invisible substance that outweighs all the ordinary matter by a factor of about 5 to 1. We can't see dark matter directly, but we know it's there because of its gravitational effects. Stars in the outer regions of galaxies orbit faster than they should if only the visible matter were providing the gravitational glue. Galaxy clusters bend light from background objects more than the visible matter alone could account for. Computer simulations of galaxy formation only work if we include large amounts of dark matter to provide the gravitational scaffolding around which ordinary matter can organize itself. This dark matter halo extends far beyond the visible disk of a galaxy, creating a spherical envelope that may be several times larger than what we can see with our telescopes. It's like discovering that every city you thought you knew actually extends into invisible suburbs, populated by residents you can't see, but whose presence shapes everything about how the visible city functions. The dark matter was likely the first component to collapse under its own gravity in the early universe, creating the gravitational wells into which ordinary matter later fell, eventually forming the stars and gas clouds we observe today. Galaxies also contain supermassive black holes at their centers, typically millions to billions of times more massive than our Sunday. These cosmic monsters sit like gravitational anchors at the galactic core, influencing the motions of nearby stars and occasionally flaring to life when material falls into them. During these active phases, the black hole's immediate surroundings can outshine the entire rest of the galaxy, creating phenomena we observe as quasars and other active galactic nuclei. Even when relatively quiet, as our own galaxy's central black hole currently is, these objects play important roles in regulating star formation and gas flows throughout their host galaxies. The various components of a galaxy don't exist in isolation but interact in complex ways that drive galactic evolution over cosmic time. Stars form from gas clouds, live their lives, and return enriched material to the interstellar medium. Supernovae and stellar winds create bubbles of hot gas that can trigger or suppress nearby star formation. The galaxy's rotation creates spiral density waves that compress gas and dust, leading to the beautiful spiral patterns we observe. Meanwhile, the dark matter halo provides the gravitational framework that holds everything together and continues to accrete material from the cosmic web, fueling ongoing galactic growth and evolution. Galaxies come in three main varieties, like cosmic architectural styles developed over billions of years of gravitational engineering. Spiral galaxies, like our own Milky Way, are the cosmic pinwheels, graceful arms sweeping out from a central bulge, adorned with bright blue stars and rosy nebulae where new suns are being born. Elliptical galaxies are the cosmic pearls, smooth and featureless, ranging from nearly circular to highly elongated, filled mostly with older, yellower stars living out their quiet middle age. Then there are the irregulars, the cosmic avant-garde, with no clear pattern or structure, often shaped by gravitational encounters with their neighbors. Each type tells a story about how galaxies form, evolve, and interact with each other across the vast stretches of cosmic time, like different chapters in the universe's ongoing autobiography written in starlight. Spiral galaxies are perhaps the most photogenic members of the galactic family, and it's easy to see why they capture our imagination. Their elegant arms seem to sweep outward from the central bulge like cosmic dancers frozen in mid-pirouette, traced by brilliant blue-white stars and glowing pink nebulae that mark regions of active star formation. These arms aren't solid structures, but rather density waves that move through the galactic disk like cosmic traffic jams, compressing gas and dust as they pass, and triggering bursts of star formation in their wake. The brightest, most massive stars born in these compressed regions are so short-lived that they die before they can drift far from their birthplaces, creating the illusion that the spiral arms themselves are made of bright blue stars. The spiral structure is maintained by a delicate balance of forces. The galaxy's rotation tries to wind the arms tighter and tighter, but various processes, including gravitational interactions with nearby galaxies, density waves propagating through the disk, and feedback from star formation work to maintain the pattern over billions of years. Some spiral galaxies show beautiful, symmetric, two-armed patterns, while others display multiple arms, rings, or more chaotic structures. Many, including our own Milky Way, are barred spirals, featuring a central bar-shaped structure from which the arms emerge. These bars appear to play important roles in funneling gas toward the galactic center and regulating star formation rates. The central bulges of spiral galaxies contain older stellar populations, typically redder and more metal-rich than the stars in the disk. These regions formed early in the galaxy's history when gas was more abundant and star formation rates were higher. Surrounding the visible disk is often a sparse stellar halo containing the galaxy's oldest stars, arranged in globular clusters that orbit the galactic center like ancient satellites carrying fossil records of the galaxy's youth. Elliptical galaxies present a completely different aesthetic, smooth, featureless, and often nearly spherical, though they can range from perfectly round to quite flattened or elongated. These cosmic eggs contain primarily older stellar populations, giving them their characteristic yellow-red color. Unlike spirals, ellipticals show little ongoing star formation and lack the organized rotation that creates spiral structure. Instead, their stars follow more random orbits, supported against gravitational collapse by their collective motion in all directions rather than the ordered circular motion found in spiral disks. The largest elliptical galaxies are among the most massive objects in the universe, containing trillions of stars and often found at the centers of galaxy clusters, where they've grown by cannibalizing smaller neighbors over billions of years. These galactic giants can be hundreds of thousands of light-years across, dwarfing spiral galaxies like our own. At the other extreme, dwarf ellipticals are among the most common galaxies in the universe, containing only millions of stars and barely visible except to the most sensitive telescopes. The formation of elliptical galaxies likely involves different processes than spiral formation. Many appear to be the products of galactic mergers, where two or more spiral galaxies have collided and merged over hundreds of millions of years. During such mergers, the organized rotation of the original spirals is disrupted. Their gas supplies are either consumed in bursts of star formation or expelled by the violence of the interaction, and the resulting system settles into the more random stellar motions characteristic of ellipticals. Irregular galaxies are the free spirits of the cosmic zoo, lacking the organized structure of spirals or the smooth symmetry of ellipticals. The large and small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches of light, are classic examples of irregular galaxies. These systems often show signs of ongoing star formation, with bright blue stellar associations and glowing nebulae scattered throughout their disorganized structures. Many irregulars appear to be either very young galaxies still in the process of organizing themselves, or older systems that have been disrupted by gravitational interactions with larger neighbors. Some irregular galaxies may be spiral or elliptical systems caught in the act of merging, their structures temporarily scrambled by gravitational tides. Others might be pristine systems that have never experienced major merger events and thus retain the chaotic structure they had when they first formed. The smallest irregular galaxies, called dwarf irregulars, often contain very young stellar populations and may represent systems where star formation has been delayed for billions of years, possibly by the ionizing radiation from nearby larger galaxies. Between these major categories lie various intermediate and peculiar types. Lenticular galaxies have the central bulges and disks of spirals, but lack spiral arms, appearing like cosmic lenses edge-on. Ring galaxies display spectacular circular or elliptical structures, often created by collision-induced density waves. Peculiar galaxies show distorted shapes, tidal tails, or other features that mark them as systems currently undergoing dramatic gravitational interactions. The distribution of galaxy types has evolved over cosmic time. In the early universe, irregular and peculiar galaxies were more common, reflecting the more chaotic conditions when galaxies were still forming and merging frequently. Over billions of years, as the universe expanded and galaxy interactions became less common, More organized structures like spirals and ellipticals became dominant. Today's galaxy populations represent a snapshot of this ongoing evolutionary process, with each type reflecting different paths through the complex landscape of gravitational forces, gas dynamics, and stellar feedback that shape galactic development across cosmic time. We live in a barred spiral galaxy called the Milky Way, our cosmic home address in the universe's vast postal system. It's roughly 100,000 light-years across, meaning light itself takes 100,000 years to travel from one edge to the other, and contains between 200 to 400 billion stars. Our solar system sits about 26,000 light-years from the galactic center, in a minor spiral arm called the Orion Arm, nestled between two larger arms like a quiet suburban street between major highways. We're orbiting the galactic center at about 220 kilometers per second, completing one full galactic year every 225 million Earth years. The last time we were in this same position, dinosaurs were just beginning to dominate the planet. It's a dizzying thought. While we experience days and seasons, our entire solar system is slowly wheeling through space on a journey so vast, it makes human history seem like a single breath. To put our galactic address in perspective, imagine shrinking the Milky Way down to the size of North America. On this scale, our solar system would be about the size of a quarter, located somewhere in the American Midwest. The nearest star to our Sun, Proxima Centauri, would be another quarter, about 700 miles away. The supermassive black hole at the galactic center would be in Hudson Bay, while the edge of the galaxy would stretch from the Atlantic to the Pacific, from the Arctic Ocean down to Central America. Even at this reduced scale, the distances between stars are so vast that most of the continent would be essentially empty space, punctuated only occasionally by these quarter-sized stellar systems. Our location in the galaxy is actually quite special, though not in the way you might expect. We sit in what astronomers call the galactic habitable zone, a region where conditions are just right for the development of complex life. Too close to the galactic center, and we'd be bombarded by dangerous radiation from the supermassive black hole and frequent supernovae from the densely packed stars. Too far out toward the galactic edge, and there wouldn't be enough heavy elements, carbon, oxygen, nitrogen, iron, to form rocky planets like Earth. These elements are manufactured in stellar cores and dispersed by dying stars, so regions that have hosted many generations of stars tend to be more enriched in the building blocks of planets and life. The Milky Way's structure reveals itself gradually as astronomers piece together observations from our embedded perspective. The central bulge, that downtown region of older stars surrounding the galactic center, appears as a bright, somewhat flattened sphere when viewed from our position. It's densely packed with red and yellow stars that formed early in the galaxy's history, along with the supermassive black hole Sagittarius A star that anchors the entire system. This central region is often obscured by dust lanes in the galactic disk, which is why we see those dramatic dark patches cutting across the Milky Way when we look toward the galactic center on summer nights. The disk of our galaxy is where most of the action happens. It's a relatively thin structure, only about 1,000 light-years thick compared to its 100,000 light-year diameter, like a dinner plate compared to a coin. This is where we find the spiral arms, traced by young blue stars, pink nebulae, and the dark lanes of dust that absorb starlight and create the intricate patterns we see silhouetted against the background glow. The spiral structure rotates around the galactic center, but not like a solid wheel. Instead, different parts of the galaxy rotate at different speeds, with the inner regions completing orbits faster than the outer regions, creating a differential rotation that helps maintain the spiral pattern over billions of years. Our particular spiral arm, the Orion Arm, is actually just a minor spur connecting two major arms, the Perseus Arm further out and the Sagittarius Arm closer to the center. It's sometimes called the local arm, which has a nice neighborly feel to it, as if we're living on a quiet side street in the cosmic suburbs. This arm contains not just our solar system, but also many of the bright stars we see in our night sky, including the stars that form the constellation Orion, which gave the arm its name. The bright blue giants of Orion's belt, the red supergiant Betelgeuse, and the brilliant blue-white star Rigel are all relatively nearby neighbors in our local galactic neighborhood. Surrounding the disk is the galactic halo, a roughly spherical region containing the galaxy's oldest stars arranged in globular clusters. These ancient stellar cities orbit the galactic center in highly elliptical paths, sometimes diving through the disk and sometimes swinging far out into the galactic countryside. Each globular cluster contains hundreds of thousands of stars that formed together early in the galaxy's history, and they serve as fossil records of conditions in the young Milky Way. The halo also contains individual stars, often called halo stars, that were likely stripped from globular clusters or small satellite galaxies that the Milky Way has consumed over its long history. Beyond the visible halo extends an even larger structure, the dark matter halo that provides the gravitational foundation for our entire galaxy. This invisible component may extend several times farther than the visible stars, creating a spherical envelope of dark matter within which our familiar spiral galaxy is embedded like a glowing ornament. The dark matter halo continues to accrete material from the cosmic web, slowly adding mass to our galaxy and occasionally delivering small satellite galaxies that will eventually be torn apart and absorbed. Our galaxy isn't alone in space, but is part of a small group of galaxies called the Local Group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and about 80 smaller dwarf galaxies. The Local Group itself is part of a larger structure called the Virgo Supercluster, which contains thousands of galaxies arranged in clusters, groups, and filaments spanning tens of millions of light years. And even that vast structure is just one small part of an even larger cosmic web that connects galaxy clusters across hundreds of millions of light years. Our cosmic address keeps getting longer and more impressive, the farther out we zoom. Earth, Solar System, Orion Arm, Milky Way Galaxy, Local Group, Virgo Supercluster, Laniakea Supercluster, Observable Universe. Perhaps the strangest thing about galaxies is that most of their mass isn't in the stars we can see, but in something we call dark matter, an invisible substance that outweighs all the regular matter by about 5 to 1. We know it's there because of how galaxies rotate and how they bend light from objects behind them, but we've never directly detected a particle of it. Dark matter is like the invisible scaffolding that holds galaxies together, providing the gravitational framework around which stars and gas organize themselves. Without it, galaxies would fly apart. Their outer stars orbit too quickly to be held by the gravity of visible matter alone. It's humbling to realize that the cosmos is mostly made of something we can't see, touch, or fully understand, a cosmic reminder that the universe still holds secrets far greater than our current knowledge can grasp. The discovery of dark matter came through careful observations of how galaxies rotate. When astronomers measured the orbital speeds of stars at different distances from galactic centers, they expected to find that stars farther out moved more slowly, just as planets in our solar system do. Mercury races around the sun much faster than distant Neptune, but that's not what they found. Instead, stars throughout the outer regions of galaxies all seem to be moving at roughly the same speed, far faster than the gravity of visible matter could account for. It was as if the planets in our solar system all orbited at the same speed, regardless of their distance from the sun, which would require some invisible mass to provide the extra gravitational pull. This flat rotation curve, as astronomers call it, suggested that galaxies contain far more mass than we can see. Either our understanding of gravity was fundamentally wrong, or there was a lot of matter out there that doesn't shine like stars or glow like hot gas. The evidence for this invisible matter became even stronger when astronomers studied galaxy clusters, groups of hundreds or thousands of galaxies bound together by gravity. The motions of galaxies within these clusters indicated that the clusters contained 10 times more mass than could be accounted for by all the visible galaxies combined. Even more compelling evidence came from gravitational lensing, a phenomenon predicted by Einstein's general relativity. Massive objects bend space-time, and this bending deflects light rays passing nearby, acting like a cosmic lens that can magnify, distort, or create multiple images of background objects. When astronomers studied the lensing effects of galaxy clusters, they found that the clusters were bending light far more than the visible matter alone could explain. The invisible mass responsible for this extra lensing was distributed in smooth halos around and between the visible galaxies, suggesting a completely different type of matter that doesn't interact with light the way ordinary matter does. Computer simulations of galaxy formation provide another window into dark matter's role. When astronomers try to simulate how galaxies form and evolve using only ordinary matter, the results look nothing like the galaxies we actually observe. But when they include dark matter in their models, with properties that match what observations suggest, beautiful spiral and elliptical galaxies emerge naturally from the calculations. The dark matter forms cosmic scaffolding, vast networks of filaments and nodes, where dark matter concentrates, and ordinary matter follows this framework, falling into the gravitational wells created by dark matter concentrations and eventually forming the stars and galaxies we can see. The nature of dark matter remains one of the deepest mysteries in modern science. We know it doesn't emit, absorb, or reflect light, which is why we can't see it directly. It doesn't interact electromagnetically the way ordinary matter does, so it doesn't form atoms, molecules, or the familiar structures of everyday matter. It seems to interact only through gravity, making it incredibly difficult to study beyond its gravitational effects on visible matter. Particle physicists have proposed various candidates for dark matter particles, exotic entities with names like WIMPs, weakly interacting, massive particles, axions, and sterile neutrinos. But despite decades of increasingly sensitive experiments, we haven't yet directly detected any of these hypothetical particles. The distribution of dark matter in and around galaxies follows patterns that seem almost organic. Computer simulations show dark matter forming vast cosmic webs, with dense nodes connected by filaments and separated by nearly empty voids. Galaxies form at the intersections of these filaments, like cities built at the crossroads of ancient trade routes. The dark matter halos around individual galaxies aren't smooth spheres, but show complex substructure, with smaller clumps and streams of dark matter that may be the remnants of smaller halos that have been disrupted and absorbed over cosmic time. Within our own galaxy, dark matter likely forms a roughly spherical halo extending far beyond the visible disk. This halo may contain substructures, smaller concentrations of dark matter left over from the galaxy's formation or from the tidal disruption of satellite galaxies. Some theories suggest that these dark matter subhalos might affect the orbits of stars in the galactic disk or influence the formation of stellar streams, providing potential ways to study dark matter's properties through its gravitational effects on ordinary matter. The relationship between dark matter and ordinary matter in galaxies appears to follow certain scaling relationships that hint at fundamental connections between these two components. The total mass of dark matter in a galaxy's halo seems to correlate with the mass of stars in the central galaxy, suggesting that star formation and dark matter accumulation are linked in ways we don't yet fully understand. Some galaxies appear to contain much less dark matter than expected, while others seem dark matter dominated, adding to the mystery of how these two components interact during galaxy formation and evolution. Perhaps most remarkably, the existence of dark matter means that the galaxy we can see all those hundreds of billions of stars, all the glowing gas clouds and dark dust lanes that create the beautiful structure we observe represents only about 1/6 of the total mass present. We're like visitors to a vast city who can only see the lights at night, unaware of the massive infrastructure, the underground systems, the framework that makes the visible city possible. The stars we see are just the glowing tips of an enormous gravitational iceberg, embedded in and shaped by this invisible cosmic scaffolding that holds our galaxy together and guides its evolution across billions of years. Within galaxies, stars are born, live their lives, and die in an endless cycle of cosmic recycling that's been going on for over 13 billion years. Giant molecular clouds, vast regions of gas and dust that can span hundreds of light years, serve as stellar nurseries where gravity slowly pulls matter together until temperatures and pressures become so intense that nuclear fusion ignites and a new star is born. These stars live for millions to trillions of years, cooking heavier elements in their cores through nuclear alchemy. When they die, sometimes in spectacular supernova explosions, they return their enriched material to the galaxy, seeding future generations of stars and planets with the elements necessary for rocky worlds and, eventually, life. We are quite literally made of star stuff, forged in the hearts of ancient suns that lived and died billions of years before our solar system even existed, then recycled through the galaxy's endless stellar generations. The stellar life cycle begins in the cold, dark depths of molecular clouds where temperatures hover just a few degrees above absolute zero. These cosmic nurseries are among the coldest places in the universe, vast caverns of gas and dust where hydrogen molecules drift in the darkness, occasionally colliding and sticking together on tiny dust grains. Gravity works slowly but inexorably in these regions, pulling matter together into increasingly dense clumps. As these clumps grow more massive, their gravitational pull strengthens, accelerating the process of collapse. What might take millions of years in the early stages can happen quite rapidly once a critical threshold is reached, as the cloud fragments into smaller pieces that will become individual stars or small stellar systems. The transformation from cold gas cloud to blazing star is one of nature's most dramatic metamorphoses. As a collapsing gas clump grows denser, gravitational potential energy converts to heat, warming the interior. When the core temperature reaches about 10 million degrees Celsius, hydrogen nuclei overcome their mutual electrical repulsion and begin fusing into helium, releasing tremendous amounts of energy in the process. This nuclear ignition marks the birth of a new star, as the outward pressure from fusion reactions balances the inward pull of gravity, creating a stable celestial object that can shine for billions of years. The mass of a newborn star determines its entire future biography. The most massive stars, those more than about 8 times the mass of our Sun, live fast and die young. They burn their nuclear fuel at prodigious rates, shining with brilliant blue-white light but exhausting their hydrogen supplies in just a few million years. When these stellar giants run out of fuel, they collapse catastrophically and explode as supernovae, events so energetic they can briefly outshine entire galaxies. These explosions scatter the heavy elements forged in the star's core: carbon, oxygen, silicon, iron, and dozens of others across hundreds of light-years of surrounding space, enriching the interstellar medium for future generations of stars. Medium-mass stars like our Sun follow a more sedate path through life. They burn their hydrogen fuel steadily for billions of years, maintaining a careful balance between gravitational collapse and nuclear pressure. Our Sun has been shining reliably for about 4.6 billion years and has enough fuel to continue for another 5 billion years or so. When Sun-like stars finally exhaust their hydrogen, they swell into red giants, gently puffing off their outer layers to create beautiful planetary nebulae, while their cores contract into white dwarf stars, dense, hot remnants about the size of Earth but containing most of the original star's mass. The smallest stars, red dwarfs less massive than about half our Sun, are the universe's ultimate energy misers. They burn their fuel so slowly and efficiently that they can shine for trillions of years longer than the current age of the universe. These stellar light bulbs will still be glowing long after more massive stars have exhausted their fuel and faded away. In the far future, red dwarfs may be the only stars left shining in a cold, dark cosmos, the final beacons of the stellar age that began shortly after the Big Bang. The elements essential for life are manufactured in stellar cores through a process called nucleosynthesis. Hydrogen fusion produces helium, but more massive stars can fuse helium into carbon, carbon into oxygen, and continue building heavier elements up the periodic table. The most massive stars develop onion-like layers in their cores, with different fusion reactions occurring at different depths until they've built up a core of iron. Iron fusion doesn't release energy but actually requires energy input, so when a massive star's core becomes predominantly iron, the nuclear fires that have supported it for millions of years suddenly go out. The core collapses in less than a second, rebounds, and drives a shock wave through the star that creates the supernova explosion. During these stellar explosions, conditions become so extreme that elements heavier than iron can be forged, including gold, silver, uranium, and many others that can't be created in normal stellar fusion. Supernovae also accelerate particles to tremendous speeds, creating cosmic rays that permeate the galaxy and may play roles in triggering new star formation in nearby molecular clouds. The shock waves from supernova explosions can compress nearby gas clouds, initiating the gravitational collapse that leads to new stellar birth, creating a feedback loop where dying stars help trigger the formation of their successors. This cosmic recycling process has been gradually enriching the galaxy with heavy elements over billions of years. The first stars that formed after the Big Bang contained only hydrogen and helium, the primordial elements created in the universe's first few minutes. These population 3 stars, as astronomers call them, were likely much more massive than typical stars today and quickly enriched their surroundings with the first heavy elements. Subsequent generations of stars incorporated these elements into their formation, and their own deaths added even more heavy elements to the galactic inventory. By the time our solar system formed about 4.6 billion years ago, the local interstellar medium had been enriched by billions of years of stellar nucleosynthesis. The gas cloud that collapsed to form our sun and planets contained about 2% heavy elements, by mass enough to form rocky planets like Earth and provide the carbon, oxygen, nitrogen, and phosphorus necessary for the complex chemistry of life. Every atom in your body heavier than hydrogen was forged in the nuclear furnace of a star that lived and died before our solar system existed, making us intimate participants in the galaxy's ongoing story of stellar birth, death, and rebirth. Galaxies aren't lonely, islands drifting in isolation. They're social creatures that interact, merge, and sometimes even cannibalize each other in a slow-motion cosmic ballet that plays out over hundreds of millions of years. When two galaxies approach each other, their gravitational embrace begins long before they actually touch, stretching and distorting their shapes, triggering bursts of star formation as gas clouds collide and compress. Sometimes, smaller galaxies are torn apart and absorbed by larger ones. Our own Milky Way is slowly consuming several smaller satellite galaxies right now. In about 4.5 billion years, we'll merge with our nearest large neighbor, the Andromeda Galaxy, in an event astronomers have poetically named Milkomeda. Don't worry, though. The distances between stars are so vast that despite this cosmic collision, the chances of any individual stars actually hitting each other are virtually zero. It'll be more like two crowds of people walking through each other in slow motion. The gravitational dance between galaxies begins when they're still millions of light years apart. Dark matter halos, those invisible scaffolds that surround every galaxy, start to feel each other's gravitational pull first, since they extend much farther than the visible stellar components. As the galaxies draw closer, these halos begin to distort each other, creating tidal forces that stretch and compress the galaxy structures within them. The first visible signs of interaction often appear as subtle warping of the galaxy disks, slight asymmetries in their spiral arms, or the formation of tidal tails, long streams of stars and gas pulled out by gravitational forces. As galaxies continue their cosmic approach, the interactions become more dramatic. Gas clouds that have been peacefully orbiting within each galaxy suddenly find themselves compressed by shock waves and gravitational disturbances. This compression can trigger intense bursts of star formation, creating brilliant blue regions of newborn stars and glowing nebulae. These starburst galaxies can increase their star formation rates by factors of 10 or more compared to isolated galaxies, burning through their gas supplies at prodigious rates. The resulting populations of massive, short-lived stars create spectacular fireworks displays as they quickly evolve and explode as supernovae, adding to the chaos and beauty of the galactic encounter. The process of galactic merger is far more complex than two solid objects simply colliding. Galaxies are mostly empty space punctuated by widely separated stars, so when they merge, it's more like two sparse swarms of bees flying through each other than two rocks hitting. Individual stars rarely collide directly, but their orbits are dramatically altered by the changing gravitational landscape. Stars that once followed orderly circular paths around their galactic centers find themselves flung onto highly elliptical orbits, some diving toward the center, others swinging far out into the galactic suburbs. During major mergers between galaxies of similar size, the original spiral structures are typically destroyed. The organized rotation that maintained beautiful spiral arms gives way to more chaotic stellar motions as gravitational torques from the interaction scramble the orderly patterns. Gas that was once distributed in a thin disk gets stirred up and heated, often forming a more spherical distribution. The end result of such major mergers is typically an elliptical galaxy, smooth and featureless, its stellar population following random orbits supported by velocity dispersion rather than organized rotation. Our own galaxy provides a perfect laboratory for studying galactic interactions because we can observe the process in exquisite detail from our embedded perspective. The Milky Way is currently in the process of consuming several smaller satellite galaxies, and the evidence is written across our night sky for those who know how to read it. The Sagittarius Dwarf Galaxy, discovered only in the 1992nd, despite being relatively close to us, is being slowly torn apart by the Milky Way's gravity. Streams of stars from this disrupted galaxy can be traced completely around the sky, forming loops and arcs that mark the orbital path of the doomed satellite. The large and small Magellanic Clouds, visible as fuzzy patches in the southern sky, are also caught in the Milky Way's gravitational web. These irregular galaxies are connected to each other and to our galaxy by a stream of hydrogen gas called the Magellanic Stream, which stretches more than halfway around the sky. This stream represents material that has been stripped from the Magellanic Clouds by tidal forces during their orbital dance with the Milky Way. Computer simulations suggest that these satellite galaxies will eventually be completely disrupted and absorbed by our galaxy over the next few billion years. But the most dramatic galactic interaction in our future is the approaching merger with the Andromeda Galaxy. Currently, about 2.5 million light-years away, Andromeda is approaching us at about 110 kilometers per second and will begin its gravitational dance with the Milky Way in roughly 4.5 billion years. Computer simulations of this encounter predict a complex multi-billion-year process during which the two galaxies will make several close passes, each time exchanging gravitational energy and losing orbital momentum until they finally settle into a single, larger elliptical galaxy. During the Milky Way-Andromeda merger, our solar system will likely be flung to a completely different part of the resulting galaxy. We might end up in the central regions, the far outskirts, or somewhere in between, depending on the chaotic gravitational interactions that occur. However, the chances of our solar system being directly disrupted are very small. The Sun will likely retain its family of planets throughout the merger, though our view of the night sky will be dramatically transformed as familiar constellations are scattered and the galaxy around us is completely reorganized. Galaxy mergers aren't just destructive processes, they're also creative ones that can rejuvenate star formation and drive galactic evolution. The gas compression that occurs during mergers can trigger the formation of massive star clusters and even stimulate the growth of supermassive black holes at galactic centers. Some of the most spectacular objects in the universe, including ultraluminous infrared galaxies and certain types of quasars, are thought to be powered by the intense star formation and black hole activity that occurs during major galactic mergers. The merger process also helps explain the diversity of galaxy types we observe today. Spiral galaxies like the Milky Way and Andromeda likely formed through the relatively gentle accretion of smaller systems over billions of years, allowing them to maintain their organized disk structures. Elliptical galaxies, particularly the largest ones found at the centers of galaxy clusters, probably grew through multiple major mergers that scrambled their original structures and created the smooth, featureless appearances we observe today. At the heart of nearly every large galaxy lurks something extraordinary. A supermassive black hole millions to billions of times more massive than our Sun, sitting like a cosmic anchor at the galactic center. These aren't the stellar mass black holes formed from collapsed stars, but monsters so large we're still not entirely sure how they formed so early in the universe's history. Our own galaxy's central black hole, called Sagittarius A, weighs about 4 million times more than the Sun and sits 26,000 light-years away from us, close enough to study, far enough to keep us safe. When gas and dust fall toward these cosmic giants, the material heats up to millions of degrees and glows brilliantly, sometimes outshining the entire galaxy around it. These active galactic cores, called quasars when they're particularly bright, can be seen across billions of light-years, serving as cosmic lighthouses that tell us about the universe's distant past. The discovery of supermassive black holes at galactic centers was one of the most surprising revelations of modern astronomy. Unlike their stellar mass cousins, which form when massive stars collapse at the end of their lives, these galactic monsters appear to have been present since very early in cosmic history. Observations of the most distant quasars, whose light has traveled over 13 billion years to reach us, show that supermassive black holes, with masses of billions of solar masses, already existed when the universe was less than 1 billion years old. This presents a puzzle. How did these objects grow so massive so quickly in the cosmic dawn? Several theories attempt to explain the origin of supermassive black holes. One possibility is that they grew from the first generation of stars, population 3 stars that formed from primordial hydrogen and helium shortly after the Big Bang. These ancient stars may have been much more massive than typical stars today, perhaps hundreds of times the mass of our Sun, and when they collapsed, they could have formed intermediate mass black holes that served as seeds for later growth. Another theory suggests that supermassive black holes formed directly from the collapse of massive gas clouds in the early universe, bypassing the stellar phase entirely. Regardless of their origins, supermassive black holes appear to play crucial roles in shaping their host galaxies. This relationship became clear through observations, showing that the mass of a galaxy's central black hole correlates remarkably well with properties of the galaxy's stellar bulge. Galaxies with more massive central bulges tend to have more massive central black holes, suggesting that the growth of these two components is somehow linked. This correlation is surprising because the black hole's gravitational influence extends only to the innermost regions of the galaxy, yet somehow its mass is connected to the properties of stars thousands of light-years away. The mechanism behind this black hole-galaxy connection likely involves feedback processes that regulate both star formation and black hole growth. When material falls toward a supermassive black hole, it doesn't fall straight in, but instead forms an accretion disk, a swirling maelstrom of gas and dust that gradually spirals inward. Friction within this disk heats the material to tremendous temperatures, causing it to glow brilliantly and sometimes launch powerful jets of particles at nearly the speed of light. These jets, along with intense radiation from the accretion disk, can heat and expel gas from the surrounding galaxy, effectively shutting down star formation over large regions. This feedback process creates a self-regulating system. When a black hole is actively feeding and growing, its energy output suppresses star formation in the surrounding galaxy. Less star formation means less gas is being recycled back into the interstellar medium by dying stars, which eventually reduces the fuel available for both new star formation and continued black hole growth. As the black hole's food supply dwindles, its activity diminishes, the feedback pressure reduces, and star formation can resume. This cyclical process may explain why galaxy growth and black hole growth remain linked across cosmic time. The Event Horizon Telescope's first image of a black hole, captured in 2019, showed the supermassive black hole at the center of the galaxy M87, revealing the glowing accretion disk and the shadow of the black hole itself. This image provided direct visual confirmation of what had been predicted by Einstein's general relativity over a century earlier. The black hole's event horizon, the point of no return beyond which not even light can escape, appeared as a dark shadow surrounded by the brilliant glow of superheated gas spiraling toward its doom. Our own galaxy's central black hole, Sagittarius A, is much quieter than the monster in M87. It's currently in what astronomers call a quiescent state, fed only by occasional wisps of gas and the stellar winds from nearby stars. However, evidence suggests it wasn't always so calm. giant bubbles of hot gas extending 50,000 light-years above and below the galactic plane, discovered by the Fermi Gamma Ray Space Telescope, may be the remnants of past periods of intense activity when Sagittarius A was actively feeding and launching powerful jets into the surrounding galaxy. The relationship between supermassive black holes and their host galaxies extends beyond simple feedback mechanisms. Computer simulations of galaxy formation show that black holes play important roles in regulating the flow of gas within galaxies, influencing the formation of spiral arms, bars, and other structures. They may also help determine when galaxies transition from active star-forming spirals to passive ellipticals, effectively controlling the evolutionary pathways that galaxies follow over cosmic time. Perhaps most remarkably, supermassive black holes serve as cosmic time machines, preserving information about conditions in the early universe. The most distant quasars we can observe are powered by black holes that formed when the universe was very young, and their properties tell us about the composition, density, and physical conditions of the primordial cosmos. By studying how these objects evolved over billions of years, astronomers can trace the co-evolution of black holes and galaxies from the cosmic dawn to the present day. The gravitational waves produced when supermassive black holes merge during galactic collisions represent another frontier in black hole science. These ripples in space-time, first detected by LIGO in 2015 from merging stellar mass black holes, carry information about the masses, spins, and orbital dynamics of the merging objects. Future space-based gravitational wave detectors will be sensitive to the much lower frequency waves produced by supermassive black hole mergers, opening a new window into the violent processes that shape galactic evolution across cosmic time. Galaxies aren't randomly scattered through space like seeds thrown by a cosmic gardener. They're organized into an intricate structure called the cosmic web, a vast network of filaments and nodes that stretches across the observable universe. Dark matter provides the invisible framework, and galaxies trace out this structure like Christmas lights strung along cosmic highways. Clusters of hundreds or thousands of galaxies gather at the intersections, connected by thin filaments containing smaller groups and individual galaxies, while vast voids, regions nearly empty of matter, stretch between them like cosmic bubbles. Our local group, which includes the Milky Way, Andromeda, and about 80 smaller galaxies, is part of a larger structure called the Virgo supercluster, which itself is just one tendril of an even larger structure called Laniakea, meaning immense heaven in Hawaiian. We're part of a cosmic address that keeps getting larger and more impressive the farther out we zoom. This cosmic web structure emerged from tiny density fluctuations in the early universe, quantum ripples that were stretched to cosmic scales during the rapid expansion called inflation. In the first few 100,000 years after the Big Bang, before stars and galaxies existed, these density variations served as gravitational seeds around which matter began to collect. Dark matter, being immune to the radiation pressure that affected ordinary matter in the early universe, was the first to respond to these gravitational calls, forming an invisible scaffolding of filaments and nodes that would later guide the distribution of galaxies we observe today. The nodes of the cosmic web, where multiple filaments intersect, became the sites of the largest gravitationally bound structures in the universe, galaxy clusters. These cosmic cities contain hundreds to thousands of galaxies held together by gravity, along with vast amounts of hot gas that fills the space between galaxies and glows at X-ray wavelengths. The largest galaxy clusters can contain the mass of 1,000,000 billion suns, making them among the most massive objects in the universe. At their centers, giant, elliptical galaxies often sit like cosmic downtowns, having grown fat by cannibalizing smaller neighbors over billions of years. Between the dense nodes and filaments lie the cosmic voids, vast regions of space that are nearly empty of galaxies. These voids can span hundreds of millions of light-years, containing only a few scattered dwarf galaxies in volumes that could encompass thousands of galaxy clusters. From our perspective, living in a relatively dense part of the cosmic web, it's difficult to imagine such emptiness. If our local group were located in the center of a cosmic void, The nearest large galaxy might be hundreds of millions of light-years away instead of the mere 2.5 million light-years to Andromeda. The night sky would be profoundly darker, containing only the stars of our own galaxy, with virtually no other galaxies visible to the naked eye. The structure of the cosmic web can be mapped by conducting large-scale galaxy surveys that measure the positions and distances of millions of galaxies across vast volumes of space. When astronomers plot these galaxy positions in 3 dimensions, the web-like structure becomes clearly visible, with galaxies strung along filaments that connect dense nodes while avoiding the empty voids. These surveys have revealed that the cosmic web exists on multiple scales, from small groups like our local group, connected by thin filaments, up to superclusters, connected by much more massive structures, spanning hundreds of millions of light-years. Our local group occupies a relatively quiet suburb of the cosmic web, sitting on a minor filament that connects to larger structures. The local group itself contains about 80 known galaxies, dominated by the Milky Way and Andromeda, with the Triangulum galaxy as a smaller but still significant member. The remaining galaxies are mostly small dwarfs, including the large and small Magellanic Clouds, various dwarf elliptical and dwarf spheroidal galaxies, and a few dwarf irregulars. Despite containing fewer than 100 galaxies, the local group spans about 10 million light-years and has a total mass of roughly 2 trillion solar masses, most of it in the form of dark matter. The local group is gravitationally bound, meaning its member galaxies are held together by their mutual gravitational attraction and will continue to interact and eventually merge over cosmic time. The largest merger event in our future is the collision between the Milky Way and Andromeda, but smaller mergers and interactions are ongoing throughout the group. The Milky Way is currently absorbing several dwarf satellites, while Andromeda has its own retinue of small companions that will be involved in the eventual mega-merger. Beyond the local group lies the Virgo supercluster, a much larger structure containing about 1,300 galaxies organized into multiple galaxy clusters and groups. The dominant component is the Virgo cluster itself, located about 50 million light-years away and containing over 2,000 galaxies, including the giant elliptical galaxy M87, with its famous supermassive black hole. The gravitational influence of the Virgo cluster affects the motion of our local group, pulling us toward it at about 600 kilometers per second, in a process that adds an extra component to the cosmic expansion we observe in more distant regions. Recent mapping efforts have revealed that the Virgo supercluster is itself part of an even larger structure called Laniakea, Hawaiian for immense heaven. Laniakea spans about 520 million light-years and contains roughly 100,000 galaxies with a total mass of about 100 million billion solar masses. The structure is defined not just by the galaxies it contains, but by the pattern of galaxy motions, which reveal the underlying gravitational flow toward a massive attractor called the Great Attractor. This mysterious concentration of mass, located behind the plane of our galaxy and thus partially hidden by dust, appears to be pulling our entire local region of the universe toward it. The cosmic web continues to evolve as the universe expands and ages. Computer simulations show that the filamentary structure becomes more pronounced over time as matter continues to flow along the gravitational channels established in the early universe. Galaxy clusters grow more massive as they accrete matter from surrounding regions, while voids expand and become emptier as their sparse matter is pulled toward denser regions. Eventually, the accelerating expansion of the universe will carry distant structures beyond our cosmic horizon, leaving future civilizations with an increasingly isolated view of their cosmic neighborhood. The cosmic web also plays crucial roles in galaxy evolution by controlling the supply of gas available for star formation. Galaxies located along dense filaments have access to fresh gas flowing along these cosmic highways, while galaxies in voids may become isolated and eventually exhaust their gas supplies. The environment in which a galaxy lives, whether in a dense cluster, a sparse group, or the cosmic countryside, significantly influences its evolutionary path, determining whether it becomes a gas-rich spiral actively forming stars or a gas-poor elliptical that has ceased star formation. Understanding our place in the cosmic web provides a profound perspective on our cosmic address. We inhabit not just a planet orbiting a star in a galaxy, but a galaxy that's part of a group, which is part of a supercluster, which is part of an even larger structure, all connected by invisible threads of dark matter that guide the flow of ordinary matter across cosmic time and space. When we look at distant galaxies, we're not just seeing across space, we're looking back in time, watching the universe's own home movies from when it was young. Light from the most distant galaxies we can observe left them over 13 billion years ago, when the universe was less than 1 billion years old. These ancient galaxies look different from modern ones, smaller, more irregular, often locked in dramatic mergers, and blazing with the fierce light of rapid star formation. They're like cosmic teenagers, energetic, chaotic, still growing into their final forms. By studying galaxies at different distances, and therefore different ages, astronomers can piece together the story of how these stellar cities evolved from small, simple collections of stars into the majestic spirals and ellipticals we see today. It's like having a photo album that shows how a city developed over billions of years, from its earliest settlements to its current magnificent skyline. The very first galaxies began forming when the universe was only a few 100 million years old, emerging from the cosmic dark ages when the first stars ignited and began illuminating their surroundings. These primordial galaxies were nothing like the grand spirals and smooth ellipticals we see in the nearby universe today. They were small, irregular, and incredibly active, forming stars at rates that would exhaust their gas supplies in just a few 100 million years. Their stellar populations were dominated by massive, hot blue stars that lived fast and died young, filling these early galaxies with the energetic radiation and explosive supernovae that would enrich the universe with its first heavy elements. Observations from the Hubble Space Telescope and other instruments have revealed that these early galaxies were engaged in a frenzy of merging and interaction. The universe was much denser then, with galaxies packed more closely together, leading to frequent encounters and collisions. These cosmic traffic jams weren't destructive but rather constructive, allowing small galaxy fragments to merge and grow into larger, more massive systems. Each merger brought new gas supplies to fuel star formation and added stellar populations with different ages and compositions, gradually building up the complex structure we see in mature galaxies today. The process of galaxy assembly wasn't uniform across the universe but followed a hierarchical pattern, with smaller structures forming first and then merging to create larger ones. This bottom-up growth is exactly what theories of structure formation predict, driven by the gravitational collapse of dark matter halos that provide the scaffolding for galaxy formation. The smallest galaxies formed first, when the universe was dense and rich in gas, while the largest galaxies we see today are often the products of multiple mergers that occurred over billions of years, gradually assembling their stellar populations from many smaller building blocks. As we look at galaxies from different cosmic epochs, we can trace the evolution of their star formation rates, chemical compositions, and structural properties. In the early universe, galaxies were forming stars at rates tens or hundreds of times higher than typical galaxies today. This cosmic star formation boom peaked when the universe was about 2-3 billion years old, an era astronomers call cosmic noon, when star formation rates across the universe reached their maximum. Since then, star formation has been gradually declining, as galaxies have consumed their gas supplies, and the universe's expansion has made it harder for new gas to fall into galactic gravitational wells. The chemical evolution of galaxies tells another compelling story visible in the light from distant systems. The first galaxies contained only hydrogen and helium, the primordial elements created in the Big Bang. But as generations of massive stars lived and died, they enriched the interstellar medium with heavier elements: carbon, oxygen, nitrogen, silicon, iron, and many others. We can trace this chemical enrichment by studying the spectra of distant galaxies, watching how the abundance of heavy elements increased over cosmic time. This gradual enrichment made possible the formation of rocky planets and the complex chemistry necessary for life, connecting the evolution of galaxies to the emergence of habitable worlds. The morphological evolution of galaxies from early irregular forms to today's elegant spirals and ellipticals reflects the interplay between cosmic expansion, gas accretion, and internal processes like star formation and feedback from supernovae and black holes. Early galaxies were irregular, partly because they were still assembling from mergers, but also because the intense star formation and supernova explosions created turbulent conditions that prevented the formation of stable, organized structures. Only as star formation rates declined and galaxies settled into more regular gas accretion patterns could the orderly rotation needed for spiral structure develop. Environmental factors also played crucial roles in galaxy evolution, with galaxies in different cosmic neighborhoods following different evolutionary paths. Galaxies in dense clusters often had their star formation quenched early as they fell into hot cluster gas that stripped away their own gas supplies. Isolated galaxies in the cosmic countryside could continue forming stars for billions of years longer, maintaining their spiral structure and blue colors. These environmental effects help explain the diversity of galaxy types we observe today and the strong correlations between galaxy properties and their surroundings. Modern deep-field observations push this cosmic archaeology to its limits, detecting galaxies so distant that their light has been traveling toward us for over 13 billion years. These observations reveal that even in the universe's first billion years, some galaxies had already grown surprisingly massive and organized, challenging our understanding of how quickly cosmic structures could assemble in the early universe. Each new generation of telescopes pushes this frontier further back in time, revealing earlier and earlier epochs of galaxy formation and bringing us closer to understanding the very first stellar cities that lit up the cosmic dawn. Not all regions of a galaxy are equally hospitable to life as we know it. There's a concept called the galactic habitable zone, sometimes called the Goldilocks zone of the galaxy, where conditions are just right for planets like Earth to thrive. Too close to the galactic center, and the high density of stars, frequent supernovae, and intense radiation from the central black hole make stable planetary systems unlikely. Too far out in the galactic suburbs, and there aren't enough heavier elements forged in earlier generations of stars to form rocky planets. Our solar system sits in what many consider the sweet spot, far enough from the center to avoid cosmic violence, but close enough to benefit from billions of years of stellar nucleosynthesis that enriched our region with the carbon, oxygen, silicon, and iron necessary for rocky worlds and complex chemistry. We live in a cosmic Goldilocks zone that's just right for life. The inner regions of galaxies present multiple challenges for life-bearing planets. Near the galactic center, stars are packed so densely that gravitational interactions between stellar systems become common, potentially disrupting planetary orbits or ejecting planets from their systems entirely. A star might approach close enough to our solar system to scatter comets from the outer regions inward, creating a cosmic shooting gallery that could pummel inner planets with catastrophic impacts. The probability of such close encounters increases dramatically in the dense stellar neighborhoods near galactic centers, where stars might be separated by distances only a few times larger than our own solar system. Even more threatening than stellar encounters is the radiation environment near galactic centers. The supermassive black holes that anchor galaxies occasionally feed on nearby gas and stars, launching jets of high-energy particles and intense radiation that can sterilize planets across thousands of light-years. During active periods, these galactic cores become quasars that outshine the entire rest of the galaxy, bathing inner regions in deadly radiation. Even during quiet periods, the accumulated stellar radiation and cosmic ray flux from densely packed stars create an environment hostile to the development and maintenance of complex chemistry on planetary surfaces. The high rate of stellar evolution in galactic inner regions also poses problems for life. Massive stars, which are more common in dense stellar environments, have short lifetimes measured in millions rather than billions of years. These stars end their lives in supernova explosions that can be lethal to life on planets within 50 to 100 light-years. In the galactic center regions, the frequency of supernovae may be so high that planetary atmospheres are continuously stripped away by shock waves and high-energy radiation, preventing the stable conditions necessary for life to emerge and evolve over geological timescales. On the opposite extreme, the outer regions of galaxies present different but equally challenging conditions for life. The primary limitation in galactic suburbs is metallicity, the abundance of elements heavier than hydrogen and helium. These heavy elements, which astronomers collectively call metals, regardless of their chemical properties, are essential for forming rocky planets and supporting the complex chemistry of life. Carbon, oxygen, nitrogen, phosphorus, sulfur, and numerous other elements must be present in sufficient quantities to form the molecules that make life possible. Heavy elements are manufactured in stellar cores through nuclear fusion and dispersed into space when stars die, either through gentle stellar winds or violent supernova explosions. This means that regions of the galaxy that have hosted many generations of stars tend to be more enriched in heavy elements than regions where star formation has been sparse. The outer reaches of galaxies, where star formation rates have historically been low, may lack sufficient heavy elements to form substantial rocky planets, leaving only gas giants or small, icy bodies in these cosmic wilderness areas. The galactic habitable zone isn't a fixed ring but has evolved over cosmic time as stellar nucleosynthesis has gradually enriched the galaxy with heavy elements. In the early universe, even the inner regions of galaxies lacked sufficient heavy elements for rocky planet formation. The habitable zone was essentially non-existent for the first few billion years of galactic evolution. As successive generations of stars lived and died, the zone of metallicity suitable for life gradually expanded outward from the galactic center, reaching our solar system's orbital radius around the time our solar system formed 4.6 billion years ago. Our particular location in the galaxy appears to be nearly optimal for life-bearing planets. We sit in the disk of the galaxy, where star formation has been active for billions of years, ensuring adequate heavy element enrichment, but we're far enough from the center to avoid the radiation and gravitational hazards of the inner regions. Our position between major spiral arms may also be beneficial, keeping us away from the massive star formation regions in the arms where supernova rates are highest, while still allowing us to periodically pass through the arms and benefit from their gravitational effects on the solar system's orbit. The concept of galactic habitable zones has implications for the search for extraterrestrial life and the distribution of habitable planets throughout the universe. If similar constraints apply to other galaxies, then the majority of potentially life-bearing planets may be concentrated in annular zones at intermediate distances from their galactic centers. This could help guide future searches for exoplanets and biosignatures by focusing attention on stars in the galactic habitable zones of nearby galaxies. However, the galactic habitable zone is just one factor among many that determine planetary habitability. Individual stellar properties, planetary system architecture, geological activity, and atmospheric evolution all play crucial roles in determining whether a planet can support life. Some planets might thrive outside the traditional galactic habitable zone if they have other protective mechanisms, such as strong magnetic fields that deflect harmful radiation or thick atmospheres that provide shielding from cosmic rays. The realization that our location in the galaxy may be special adds another layer to the cosmic perspective on life and intelligence. Not only do we live on a planet in the habitable zone around our star, but our entire solar system resides in the habitable zone of our galaxy. This double Goldilocks situation suggests that life-bearing planets may be more rare and precious than we might otherwise expect, scattered like cosmic oases in the vast desert of space, concentrated in those special regions where conditions are just right for the long, slow process of biological evolution to unfold over billions of years. What does the future hold for galaxies like ours? In the shorter term, the next few billion years, our Milky Way will continue its slow dance with gravity, gradually consuming smaller satellite galaxies while preparing for its eventual merger with Andromeda. Star formation will continue, but more slowly as the galaxy's gas supply is gradually depleted. In the much more distant future, trillions of years from now, the universe's expansion will accelerate, carrying other galaxy clusters beyond our cosmic horizon until our merged galaxy becomes an island of light in an increasingly empty and dark cosmos. Eventually, even within our galaxy, star formation will cease as gas is exhausted, and the galaxy will fade to a collection of long-lived red dwarf stars, white dwarfs, neutron stars, and black holes. But that's so far in the future that life itself may have evolved into forms we can't imagine, or perhaps spread throughout the galaxy in ways that make these cosmic changes irrelevant. The immediate future of our galaxy is relatively well understood through computer simulations and observational studies of similar systems. Over the next billion years, the Milky Way will continue to accrete small satellite galaxies, adding their stars to our outer halo and triggering modest bursts of star formation as their gas clouds are compressed during the merger process. These events will add perhaps 10% to our galaxy's total mass, gradually building up the stellar halo and possibly disturbing the orbits of stars in the outer disk regions. Meanwhile, our galaxy's own star formation will continue at roughly its current rate, converting the remaining gas in the disk into new generations of stars at a pace that could sustain current activity levels for several more billion years. The most dramatic change in our galactic neighborhood will be the collision with Andromeda, scheduled to begin in about 4.5 billion years. This event will fundamentally transform both galaxies over a period spanning several billion years. The first close approach will gravitationally distort both systems, launching streams of stars into intergalactic space and triggering intense bursts of star formation as gas clouds collide and compress. The galaxies will then separate briefly before swinging back for additional encounters, each passage further scrambling their original structures and transferring orbital energy until they finally settle into a single, larger system that astronomers have dubbed Milkomeda. The merged galaxy will likely be an elliptical system, lacking the organized spiral structure of its parent galaxies. Most of the gas that doesn't get consumed in merger-triggered star formation will be heated and expelled, leaving behind a population of older stars following more random orbits. Our solar system will survive this cosmic collision unscathed. The chances of direct stellar collisions are vanishingly small due to the vast distances between stars, but we'll find ourselves in a completely different galactic environment, possibly relocated to the outskirts of the new system, or even ejected into intergalactic space. Looking further into the future, the fate of galaxies becomes tied to the ultimate destiny of the universe itself. Current observations suggest that the universe's expansion is accelerating, driven by the mysterious dark energy that appears to permeate all of space. This acceleration means that galaxy clusters will eventually be carried apart by cosmic expansion, with each cluster becoming increasingly isolated from its neighbors. Over timescales of hundreds of billions of years, the cosmic web of galaxy clusters and filaments will dissolve as individual clusters recede beyond each other's cosmic horizons. Within isolated galaxy clusters, gravitational interactions will continue to drive evolution over these vast timescales. Galaxies will continue to merge with their neighbors, gradually building up a few massive central galaxies while ejecting others from the cluster entirely. Computer simulations suggest that after about 1 trillion years, most galaxy clusters will have collapsed into single, giant, elliptical galaxies surrounded by sparse halos of ejected stars and dead stellar remnants. These cosmic islands will be all that remains of what were once rich clusters containing hundreds or thousands of individual galaxies. Star formation will gradually wind down across the universe as the supply of gas available for creating new stars becomes depleted. Galaxies will consume their remaining gas reserves over time scales of tens to hundreds of billions of years, after which no new stars will form. The universe will enter what cosmologists call the degenerate era, dominated by long-lived red dwarf stars, white dwarf remnants of sun-like stars, neutron stars, and black holes. The red dwarfs will be the last stars shining, burning their hydrogen fuel so slowly that they can continue for trillions of years, providing the final sources of energy in an increasingly cold and dark cosmos. Even the longest-lived stars will eventually exhaust their fuel, leaving behind white dwarf remnants that will slowly cool and fade over hundreds of trillions of years. Proton decay, if it occurs as some theories predict, will gradually disintegrate even these stellar corpses over unimaginably long timescales of 10 circumflex 34 years or more. Eventually, only black holes will remain as the dominant gravitational structures in the universe, slowly evaporating through Hawking radiation over timescales so vast that the current age of the universe seems like an instant by comparison. Yet these cosmic timescales are so enormous that they dwarf not just human history but the entire future evolution of stars and planets by factors of millions or billions. Long before galaxies fade and stars burn out, life and intelligence may have evolved and spread in ways that fundamentally alter the trajectory of cosmic evolution. Advanced civilizations might learn to harvest the energy of entire stars, artificially extend stellar lifetimes, or even create new stars from accumulated matter. The biological and technological evolution that could occur over galactic timescales might make our current understanding of cosmic evolution as quaint as a medieval map of the world. So what is a galaxy, really? It's many things at once. A gravitational sculpture carved by dark matter and shaped by billions of years of stellar birth and death. It's a cosmic city where stars live in neighborhoods defined by age, chemistry, and stellar social circles. It's a time machine that preserves the history of the universe in the light of its oldest stars and the composition of its gas clouds. It's a recycling center where the ashes of dead stars become the seeds of new worlds. And for us, it's home, not just our local planetary home, but our vast cosmic neighborhood, the stellar community that gave birth to our sun and every atom in our bodies. When you realize that you're part of this magnificent structure, that every breath you take contains atoms forged in the hearts of ancient stars and dispersed by stellar winds across the galaxy, the boundary between you and the universe begins to dissolve in the most wonderful way. Perhaps the most profound realization about galaxies is that they represent a fundamental level of cosmic organization, a scale where the universe's creative forces come together to build structures of breathtaking beauty and complexity. They're not just collections of stars, but integrated systems where every component influences every other component across vast scales of space and time. The supermassive black hole at the center regulates star formation thousands of light-years away. Supernovae in one spiral arm enrich gas clouds that will form planets in another arm millions of years later. The gentle gravitational stirring of dark matter halos guides the flow of gas that feeds stellar nurseries and maintains the galaxy's ongoing evolution. Galaxies also represent laboratories where the universe experiments with structure and form. Each galaxy is unique, shaped by its particular history of mergers, star formation episodes, and environmental influences. Some became elegant spirals with graceful arms traced by young blue stars. Others evolved into smooth ellipticals filled with ancient stellar populations. Still, others remained irregular, their structures disrupted by interactions or frozen in states of perpetual youth. This diversity reflects the many pathways that gravitational systems can follow when given billions of years to evolve under slightly different initial conditions. The temporal aspect of galaxies is equally remarkable. They're simultaneously ancient and young, containing stars that formed over 13 billion years ago alongside stars being born today. This spans of cosmic time means that galaxies serve as archaeological sites, preserving evidence of the universe's entire history since the first stars ignited. The oldest globular clusters carry chemical signatures from the early universe when only hydrogen and helium were abundant. Intermediate-age stellar populations record periods of active star formation and galaxy interactions. The youngest stars tell us about current conditions in the interstellar medium and ongoing processes of stellar birth. Galaxies are also bridges across the cosmic scale hierarchy, connecting the microscopic realm of atomic and nuclear physics to the largest structures in the universe. The nuclear fusion that powers individual stars collectively determines galaxy colors and brightnesses. The electromagnetic radiation from countless stellar atmospheres creates the complex spectra that reveal galactic compositions and motions. Meanwhile, galaxy interactions and mergers shape the cosmic web on scales spanning hundreds of millions of light-years. Understanding galaxies requires integrating physics across more than 40 orders of magnitude in scale, from quantum mechanics to cosmology. For conscious beings like ourselves, galaxies provide the essential context for existence itself. The heavy elements manufactured in galactic stellar populations over billions of years created the chemical diversity necessary for complex molecules, rocky planets, and ultimately life. The relative stability of our galaxy's disk provided a safe harbor where planetary systems could evolve undisturbed for billions of years. The gradual enrichment of the interstellar medium with heavy elements set the stage for the formation of solar systems capable of hosting habitable worlds. We exist because our galaxy has been patient, stable, and generous with the products of its stellar alchemy. The aesthetic dimension of galaxies shouldn't be overlooked either. They represent some of the most beautiful structures in the universe, with their spiral arms traced by brilliant blue stars and rosy nebulae, their central bulges glowing with the warm light of ancient stellar populations, and their dark lanes of dust creating intricate patterns against the background starlight. This beauty isn't accidental, but emerges from the same physical processes that make galaxies functional as stellar ecosystems. The spiral density waves that create elegant arm patterns also trigger the star formation that illuminates those arms. The smooth profiles of elliptical galaxies reflect the gravitational processes that mix their stellar populations during formation. Galaxies also embody one of the universe's most important principles: emergence. Complex, organized structures arise from simpler components following basic physical laws. Dark matter particles, following only gravitational attraction, create the invisible scaffolding that supports visible galactic structure. Gas clouds, responding to pressure, gravity, and magnetic fields, organize into the spiral patterns that guide star formation. Individual stars, burning nuclear fuel according to the laws of physics, collectively create the chemical evolution that transforms galactic compositions over cosmic time. None of these components knows about the larger structure they're creating, yet their interactions give rise to galaxies of stunning complexity and beauty. Perhaps most remarkably, galaxies have given rise to observers capable of understanding them. Through us, the universe has developed the ability to study and appreciate its own structure. We are arrangements of galactic matter that have organized themselves into forms capable of consciousness, curiosity, and wonder. When we study galaxies, we're really studying our own cosmic ancestry and current environment. The iron in our blood was forged in stellar cores within our galaxy. The calcium in our bones was scattered by supernovae that enriched our local interstellar medium. We are not separate from galaxies, but temporary expressions of galactic matter that has learned to contemplate its own magnificent cosmic context. And so, dear cosmic traveler, we reach the end of our gentle journey through the stellar cities we call galaxies, though really, we've only just begun to explore our vast galactic home. We've wandered from the familiar band of the Milky Way overhead to the invisible scaffolding of dark matter, from stellar nurseries where suns are born to the supermassive mysteries at galactic hearts. Along the way, we've seen that galaxies are not just distant lights in the sky, but living, breathing, evolving communities of stars, and that we are not separate from them, but part of their ongoing story. So let me ask you once more, as I did when we began, where are you watching from tonight? And when you look up at your patch of sky, can you feel it now, the slow, ancient rotation of our galaxy carrying you through space? If this cosmic voyage brought you peace, if the knowledge that you're part of something so magnificent helped quiet your mind, please consider liking this video and sharing it with someone who might need this gentle reminder of their place in the cosmos. Sleep well, fellow star stuff, in the arms of the Milky Way. It's remarkable how different the night sky feels when you understand what you're really seeing, isn't it? That faint band of light stretching overhead isn't just a pretty celestial decoration, but the edge-on view of our galactic home. Billions of distant stellar neighbors whose light has been traveling toward your eyes for thousands of years. Each point of light represents an entire stellar system, possibly with its own family of planets, its own story of birth and evolution, its own chapter in the grand narrative of galactic development. And you, sitting there in the quiet of evening, perhaps wrapped in a blanket, perhaps sipping tea, you're part of that same story. A temporary arrangement of galactic matter that has somehow organized itself into a form capable of wonder. Tonight, as you settle into rest, remember that you're not just lying still on a planetary surface. You're passengers on a small world that's spinning through space at tremendous speeds, orbiting a star that's racing around the center of a galaxy that contains hundreds of billions of other stars. Right now, as your breathing slows and your thoughts begin to soften, You're traveling at over 200 kilometers per second around the galactic center, following an orbital path that takes 225 million years to complete. The last time our solar system was in this exact position, dinosaurs were just beginning to diversify and spread across Earth. It's a journey so vast and so ancient that it puts all our daily concerns into a beautifully calming perspective. The galaxy that cradles us is more than just our cosmic neighborhood, it's our family tree, our history book, and our future home, all rolled into one magnificent structure. Every atom in your body, heavier than hydrogen, was forged in the nuclear furnaces of stars that lived and died billions of years before our sun even formed. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was manufactured in stellar cores somewhere in our galaxy and then scattered into space by stellar winds and supernova explosions. You are quite literally made of star stuff that has been cycling through the galaxy for eons, and after your current configuration of atoms moves on to other adventures, they'll continue to be part of the galaxy's ongoing story of creation and renewal. There's something deeply comforting about this cosmic perspective, especially as the day winds down and we prepare for sleep. When the worries and stresses of daily life feel overwhelming, when the future seems uncertain or the present feels chaotic, it can be wonderfully grounding to remember that we're part of something so much larger and more enduring than our immediate concerns. The galaxy has been here for over 10 billion years, patiently nurturing countless generations of stars, and it will continue long after our brief human moment has passed into the cosmic background. Our individual anxieties, while important to us in the moment, exist within a context so grand and so patient that we can afford to let them rest for a while. As you drift toward sleep tonight, let yourself feel connected to this vast stellar community that surrounds us. Somewhere out there in the galactic disk, new stars are being born in glowing nebulae, their nuclear fires igniting for the first time and beginning lifetimes that may span billions of years. Other stars, ancient beyond imagining, are gently puffing off their outer layers, returning enriched material to the interstellar medium that will seed future generations of stars and planets. Supermassive black holes are quietly regulating the flow of gas and energy through their galactic domains, while dark matter halos provide the invisible infrastructure that holds everything together in a cosmic dance of gravity and motion. The galaxy is patient in ways that can teach us about patience. Its processes unfold over timescales so vast that entire civilizations could rise and fall during what amounts to a minor fluctuation in galactic evolution. This perspective doesn't diminish the importance of our human-scale experiences, our loves, our dreams, our daily joys and sorrows, but it does place them within a context that can be profoundly calming. We're part of something that operates on timescales so grand that our most persistent worries are less than fleeting whispers in the cosmic conversation. So as your eyes grow heavy and your breathing deepens, remember that you're not alone in the darkness. You're surrounded by hundreds of billions of stellar companions, each one a distant sun burning in the cosmic night, each one part of the same magnificent galactic family that gave birth to our own sun and planets. Let the galaxy sing you to sleep with its ancient lullaby of spinning stars and slowly orbiting dark matter, a song that's been playing for billions of years and will continue long after our current concerns have faded into the peaceful darkness of cosmic time. Rest well, cosmic citizen, knowing that you're home among the stars, cradled in the gentle arms of our galactic island as it glides through the infinite sea of space and time.